Well, we started with grade 9 review, right? So we learned about subatomic particles, and then we started talking about modeling. And what was the first model that we learned? The Bohr models, right? For example, we learned about, let's draw out chlorine, for example. Chlorine has how many electrons in a neutral atom? It has 17. So we started drawing Bohr diagrams, and then we utilized these Bohr diagrams in order to talk about ions, the first thing we learned in grade 10. Now, what does chlorine want to do? Why do atoms form bonds? That big idea.
To satisfy its outer shell.
Yeah, to satisfy, in order, aka to have a full outer shell. Right? They want to have a full outer shell and look like their nearest noble gases because do the noble gases really react with other elements? No. Right? They're stable, they don't need to react, they already have a full shell. So, we talked about how chlorine wants to gain an electron. Now, I have some students that are still struggling with the idea of where these charges come from. Well, how many protons does chlorine have? 17. Right? How many electrons did it have in a neutral atom? 17, right? We're going to keep coming back to this idea of grade 9 electricity. If it's neutral, it has the same number of positive negatives, so is 17. When chlorine becomes an ion, when it gets a full shell, what happened? It gained an electron, so has now 18 electrons. That's why it has that -1 charge. Right, so again, key ideas here. Atoms form bonds to get a full shell of outer electrons. Their charge comes from how many electrons they lose or gain. If we look at an element on the other side, say like aluminum, for example, how many valence electrons does aluminum have? How many electrons in total does aluminum have?
13.
13. So how many valence electrons does it have?
3.
It has 3 valence electrons, right? So what does aluminum want to do?
Lose 3.
Wants to lose 3 electrons, right? And this is where we had that idea of, okay, well, in an ionic bond, charges do need to balance out. So we start talking about electrons donated and received, right? Aluminum is going to donate an electron. Now is the chlorine happy? Yes. So the aluminum is not, so we need to do what? Add another chlorine, then add another chlorine. That was super, super tedious, so we decided, hey, let's not draw Bohr diagrams anymore. Because what are the only electrons that matter when we're talking about bonding? The valence electrons. So what was the next model we learned?
Lewis dot diagram.
Yeah, Lewis dot. So we started saying, okay, well, we only really need to show our valence electrons. Because the other inner electrons don't really affect its reactivity. So we started showing, okay, electron transfer with just Lewis dots. And again, we're illustrating the exact same principle. Right? We're just showing atoms getting full shells of outer electrons and determining their charges as a result. So here's our aluminum. And if we look, what happened to our aluminum atom? How many protons does it have?
13.
It has 13 protons. And how many electrons did it have when it was a neutral atom?
13.
Yeah, it had 13. Now, what did we do in order to get a full shell? We lost 3 electrons to get a full shell, which means that what is the charge on our aluminum? 3 plus. Right? So this is where these charges come from. Now, if you are struggling with binary ionic compounds, if you are struggling with coming up with those chemical equations using my mathematical way, you need to take a step back and start using Lewis dots. You really need to understand where those charges come from. It's essential. Right? Maybe Lewis dots are even confusing you and you're not sure where those charges come from. Well, then you need to draw Bohr diagrams. Right? You really need to understand that key part of chemistry. It has to be ingrained in you. Why do atoms form bonds? To get full outer shell of electrons. And remember, atoms are lazy. So if you have less than 4 valence electrons, what are you going to do? You are going to lose electrons to look like your nearest noble gas. For example, calcium has how many valence electrons? 2. It's going to want to lose those 2 electrons so that it can look like which noble gas? Argon, right? When I say look like, I mean the same electronic configuration, right? The same number of electrons. So that is super important. And often I lose a lot of students when we move from this to solving it mathematically. So then we explored, okay, well, drawing models is really nice for visualizing and talking about the theory, but it's still pretty slow, right? It's not the ideal way to do this. So then we explored, well, what happens if we try to solve this mathematically, when we think logically about that big idea, right? Because in ionic bonds, charges have to balance out. So then we started exploring, okay, well, let's say I had a compound like, we'll just use the exact same one. Aluminum chloride. We already figured out its chemical formula using models. What was it? I just showed it to you. What was it? How many chlorines did I have for each aluminum?
3.
Yeah. So it was, for each aluminum, it was 3 chlorines. Right? That was the model I just showed you. But then we moved into talking, okay, how can we figure this out using math? What was step 1 for binary ionic compounds? Charge, right? Now we established where those charges come from. When we lose electrons, we become more positive. Gain electrons become more negative. What was the charge on aluminum when we make an ionic bond?
3.
3 plus. And how about chlorine?
1.
Yes, 1 what? 1 negative. Now what is the next question we ask? Sorry? How many? No, that's not the next question we ask. That's the last question we ask. What's the next one? LCM, which represents what? Yes, which the lowest common multiple tells us what? Excellent. Our total number of electrons donated received, our total charge, right? It's going to tell us our total positive charge and our total negative charge. So what is the LCM between 1 and 3? It's 3. So in total, 3 electrons donated, 3 received, 3 positive, 3 negative. And then we asked that question, Carissa. You said it before?
How many?
Oh, was it you, Kara? Sorry. How many? How many? How many of each of my ions do I need to balance my charges out? How many aluminums do I need? 1. And how many chlorines do I need? Chloride ions. We need 3, right? Each chloride ion has a charge of -1. We need 3 to have a charge of -3, right? Where we get our compound AlCl3. Now, if I want to go from formula to name for binary ionic, that should be just absolutely free marks on your test. Because really, what are the rules? If I gave you, for example, let's say this, MgS, what would you call that? Yeah, magnesium sulfate. What did you do there? What were the rules? Do you change the name of your cation? No. What do you do to your anion? You add the suffix I, right? So naming binary ionic compounds should be completely free marks, because with any modicum of practice, you'll obviously ingrain this into your mind. Now, Then we moved into what I would think is probably the most challenging thing when it comes to bonding, which is multivalent metals. I'm going to compile the two things, complex ions in one big thing, so polyatomic and multivalent. And I honestly think this is probably the hardest skill we've learned so far, which is what if I gave you a compound that looks like, let's say, this. We'll say that. How would I name that compound? Right? Because in binary ionic chemical formulas, they're really easy to name, right? You don't change the name of your cation, and you add I to your anion. In this case, however, do we know the charge on vanadium? No, right? The whole point of coming up with the stock system for naming multivalent metals was that we don't know the charge on our metal, and we need to figure it out in order to name it properly. So how do I figure out the charge on vanadium?
We find the charge on the anion.
Yeah, exactly. We need to work backwards through our anion, okay? Because we do know the charge on our anion. So that is the key to multivalent metals. Because we know the charge on our anion, and we know how many of each ion we have, we can work backwards to figure out the charge on our metal. And again, this is a challenging skill because we are kind of reversing those questions and working backwards. So we don't know the charge on vanadium, but we do know the charge on this ion. First off, what is that ion? Sulfate. How can you tell if a compound contains a polyatomic ion? How can you tell?
It has two elements in
More than two. If it has two, it's binary, right? Every other compound we're going to look at this semester is going to be a binary compound. All of the covalent compounds we explore are going to be binary covalent. So if you see a chemical formula that has more than two different elements in it, then you know you have a polyatomic ion that you have to check your table of ions for. So you're right, we have sulfate. What is the charge on sulfate? 2 negative. So now I have to work backwards through that anion. Now let's reverse those two questions, working backwards. So we know how many of each ion we have in our compound. We have 1 vanadium, and we have how many sulfates?
4.
We don't have 4.
2.
We have 2. Remember, when we're talking about polyatomic ions, if you have more than one ion, you must put it in brackets and indicate how many with a subscript outside of it. Right? Too often I'll see students do this. What is that telling us?
There's 42 oxygen.
Yeah, there's 42 oxygens. That's crazy, right? That's impossible. So you have to be careful when you're working with polyatomic ions. Right? They're a single unit. You cannot change the formula. Right? They are a group of atoms covalently bonded together that carries a net charge. So since we're reversing those questions, what is the next question here? Total. Right? We need to know, just like we use the LCM here, just like how we use the LCM in binary ionic, we need to now explore the total charges so that we can work backwards and get to the charge of vanadium. Because remember, the total charge must be the same in terms of positive and negative. It must balance out. So if we have 2 sulfates, right, and each sulfate wants to gain 2 electrons, in total, how many will be gained? 4. Right? So in total, we have a charge of 4 negative. Now, does the charge on the other end have to be the same? Do we have to have 4 positive?
Yes.
Yes.
Yeah, the charges need to balance out. So it must be 4 positive. Now let's do that last step working backwards. If we must have a charge of 4 positive, aka lose 4 electrons, and we have 1 vanadium, how many electrons must that 1 vanadium lose? It has to lose 4. So then what is the name of this compound?
Vanadium for sulfate.
Exactly. It's vanadium 4 sulfate. And thank you for saying sulfate and not sulfide, because what do we never do to the name of our polyatomic ion? Yeah, we don't change it, right? We don't add that suffix "ide" because we will never change the name of our polyatomic ion. So that is effectively everything we've learned so far, condensed into like 20 minutes. Does anyone have any questions?